Okay, welcome back. So last time we talked about a problem of combinations with restrictions of counting the number of 0 1 sequences which have no two successive ones, and we found, so we called that sequence f of n, so it is the number of 0 1 sequences of length n with no successive ones, and we tabulated the first few values of f of n. So here's what we got. So here's n, and here are the various values of n. So if n is 1, it's 2, and so on. Okay, and the rule for forming the next value of f is to just take the sum of the two preceding values. Okay, and the sequence here 2, 3, 5, 8 and so on is actually, well, it's almost the famous Fibonacci sequence of numbers. So we'll just briefly recall what the Fibonacci sequence is. So the Fibonacci numbers or the Fibonacci sequence are often denoted capital F of n. Okay, so what's capital F of n by definition? Well, it's given by the following two pieces of information. Firstly, it has the same recurrence that we wrote out for f of n, but the initial conditions are different. So f of 1 turns out to be 1 and f of 2 is also 1. Okay, so it starts at 1 1, and then when you form the next term, it is the sum of the two preceding. So the Fibonacci sequence looks like this: n versus fn. So 1, 2, 3, 4, 5, 6 and so on. So this is 1 1 followed by 2, 3, 5, 8, etc. So observe that from here on what you have are just the values of f of n. Okay, so observe from this table it's clear that the number f of n that we are counting is just f, the Fibonacci number n plus 2. Okay, so this is for all n at least 1. Okay, so the sequence that we've constructed is really just the Fibonacci numbers, but starting with the third Fibonacci number, which is the number 2. Okay, and so now here's another interesting problem going back to our combinations with restrictions. Let's count it with a somewhat, in a somewhat more finer way. So let's do the following. Let's not just look for the number of 0 1 sequences of length n with no successive ones. Let's also impose a further condition. So find the number of 0 1 sequences of length n with no successive ones. So that so far it's the same condition, but let's impose one further condition, that it containing exactly k ones. Okay, so we have a further parameter k, and we now want our sequence to have length n, and also it should have exactly k ones. Okay, so well, if it has k ones, what does it mean? Of course it means that the rest of the entries are zeros and n minus k zeros. Okay, so let's give this number a name. So this number here, let's call it maybe, instead of just f of n, it has an additional parameter k, right? So there is, so maybe we shouldn't even call it small f. So let's call it gh, h of n comma k. Okay, so there are two parameters n and k, and the value of course will depend on both of them. Okay, so let's try and do this computation. Let's find the number of sequences. Now what is it that we need to do? So this problem is actually somewhat simpler than trying to do the full problem, the original problem, in the following sense. So we know already the profile of our string. We know how many zeros and how many ones it contains. So observe, our string has n minus k zeros. So let's write down the zeros first. So here's the string in which I've not yet written the ones. So observe I have n minus k zeros. And now let's worry about where the ones can occur, right. So what we know is that the ones cannot occur in successive positions, right. So which means that anytime there is a 1, then what you need to have right after it is a 0, right. So if you now ask where can the ones be positioned in amongst the zeros, so just for the moment imagine that there are gaps between the zeros. So between each successive pair of zeros, imagine there is a gap. Now the ones can occupy positions in these gaps, right. Where can the ones live? Well, having a 1 here is okay, or having a 1 here is fine, here is okay. Now what you cannot have is to have two ones occurring right after each other. So in other words, you should think of there being exactly room for a single entry between two zeros, right. There is just a single gap there. So here's a way of thinking about this string. The ones can only occupy the gaps. Okay, so in our string the ones can only occupy the gaps. Now observe, since there are n minus k zeros, there are n minus k plus 1 gaps, and so amongst these you need to pick out k gaps. So the ones can occupy, there are k ones, so the number of choices so the number of allowed strings is just the number of ways of choosing k gaps from amongst these n minus k plus 1 gaps. Okay. So what you have is the number h of n comma k is exactly given by n minus k plus 1 choose k. Right? These are the number of ways of picking k gaps out of the total number of gaps. And so what does this give us? Well, firstly, that this problem is easier to solve. But here's another very interesting consequence of this. Observe that the total number of 0 1 sequences with no successive ones, well, the total number of each sequence must have some number of ones. It has k ones, and what is k? K can be any number between 0 and n. Okay. So in fact here's the equation which says take a sequence, look at how many ones it has, the number of ones has to be something between 0 and n. So that proves that f of n is exactly this sum. Okay. So what does that mean? It says that, so here's our conclusion. We just said that this is just the n plus second Fibonacci number. Okay, so from our analysis, here's what we have concluded, that the n plus second Fibonacci number is exactly a certain sum of binomial coefficients. And so recall that the binomial coefficients are usually arranged in the form of Pascal's triangle. So I have 1 1 1 1 2 1 and so on. And so what we have here is just, so what it says really is the following. If you take these sort of diagonal sums, so I take 1 2, I take So if you sort of add up these so called diagonals, what you get are just the Fibonacci numbers. So this is 1 1, that's a 2, this is a 3, 1 3 1 is a 5, 1 4 3 is an 8, and so on. Okay, so you can actually obtain the Fibonacci numbers from the Pascal's triangle by summing up along these diagonals in some sense. Okay, so now here's another problem. Okay, so here's another problem. It says the following: you have an interval of length n. So imagine that you have, say, between 0 and n. So you have this interval, and now what you want is to fill this up with blocks. By a block we mean, well, there are two kinds of blocks. There are short blocks and long blocks. A short block is of length 1. So imagine that say between 0 and 1, a filling like this will be a filling by a short block. Between, say, after a short block I want to fill it with a longer block. So between 1 and 3 I have a long block. So I could fill, say, with 2 short blocks and then follow it up with a long block and so on. Okay, so imagine you had to fill up this interval between 0 and n by a succession of short and long blocks, and the question is, in how many ways can this be done? Okay, so let's give this a name. Let's say the number of ways of doing this is, let's say, g of n. So of course it depends on n. And so here's the observation. We could of course try this out for some small values of n. So if you look at let's see, n. So if n is 1, what are the possible configurations? You can only have a short block because, well, the total interval has length 1, so you can only fill it with a short block. If n is 2, you have an interval of length 2, which you can either fill with 2 short blocks or with a single long block. Similarly, if n is 3, you can either have 3 short blocks or a short block followed by a long block or a long block followed by a short block. Okay, so, well, what are these numbers? The total number g of n, in this case 1, in this case 2, in this case it's the 3, and so on. Okay, so I'm not really going to write out the remaining values. Now here's the interesting observation. So if you do this, so if you sort of look at what happens for the next few values, here's what you will find, that it actually gives you back the same Fibonacci sequence. Okay, so 1 2 3 5 8 and so on. So here again there is an appearance of the Fibonacci sequence, and what we'd like to do, well, to try and solve this problem, you could try and proceed the same way, try and show that it has the same recurrence relation and so on and so forth, but I want to use this to demonstrate a certain form of proof called the proof by bijections. So here's the claim that we will now prove that this number g of n is the same as, so here's our claim. Let's prove that g of n is actually the same as let's call it f of n minus 1. Okay, this is at least for n at least 2. Remember, f counts the number of 0 1 words, strings of length n with zeros and ones which do not have 2 successive ones. So let's prove that the number of short and long fillings is in fact the same as number of 0 1 strings. Okay, and I will sort of do this by example. So let us take the case n equals 4, for which we have the following short and long strings, or maybe we will start with n equals 3. Imagine, so let us see, n equals 4 has 5, so let us do n equals 4. So I have a total interval of length 4, so I have 4 short strings, maybe I have 2 short and a long string, I have a short, long, short, I have long, short, short, or I have 2 longs. Okay, so these are all the ways in which I can make up a total length 4 using just short and long strings. Now this number, the number of such configurations is exactly counted by, so I am going to take n equals 4. So the number of allowed configurations of shorts and longs is counted by g of n. Okay, so g of n is 5, g of 4 is 5 here. On the other side, I am going to write out 0 1 sequences. Okay, so what I want is the following. I am going to write out 0 1 sequences, and these are 0 1 sequences, so these are short long sequences, and on the other side I am going to write 0 1 sequences, and but then I am going to write it for n equals 3, or yeah, I am going to write it for n equals 3. So what are the allowed 0 1 sequences for n equals 3? Well, that is all 3 zeros, 0 1 0, let us see, 0 0 1, 0 1 0, 1 0 0, 1 0 1. So there are 5 of them, right? And this is really what I am going to prove, that the number of short long sequences is the same as the number of 0 1 sequences with one smaller length. So how do we do this? So what is the proof by bijection? What you need to do is to give a recipe which to each of these sequences should map something in the other set, okay, and a recipe which should work for all values of n, not just for some specific values. So here is the here is the algorithm. So let us do this by going via an intermediary. So I will define the following map to each sequence of short and long. Let us do the following. Wherever you see a short, so replace s by a 0, and wherever you see a long sequence, you replace it by 1 0. Okay, so think of it as a code. Wherever there is a short, you replace it just by a 0, and a long by a 1 0. So if I do this, what do I get? So here's my code function. So short becomes all shorts are all zeros, short short long, short short long, short long short, long means 1 0, short short, and 2 longs is 1 0 1 0. Okay, so what I have done is via this encoding function I have converted the string of shorts and longs into a string of zeros and ones, but observe I have a string which is of length 4 now. So that is the reason I said this is an intermediary step. What I now have is strings of length 4, but here is the key observation. All of these strings, observe, will always have to end with a 0. Okay, I am not going to get all possible strings here because all of them are forced to end with a 0. And why is that? Because if I see a short, I am going to put a 0. If I see a short in the end, I will put a 0, and if I see a long, I am going to put a 1 0 anyway, right? So what I am going to get is always a 0 at the end. So what I do is I just delete that 0. After all, I know all of them are zeros, so let me get rid of all those zeros. Okay, so here is the recipe. You first encode this via zeros and ones in that manner, and then you get rid of all the zeros at the end. Okay, by doing this, what you get is exactly a map here. So I am going to send SSSS to 3 zeros, SSL will go to 0 0 1, and so on and so forth. Okay, so what I have is actually a bijection between these two sets, a map which is a one-to-one correspondence. Each thing here maps to a single thing there, and everything there comes from, is mapped to by something from here. Okay, and so check that this in fact works in general. So check this always works, no matter what my n is. Okay, so this methodology of proof is often what's called a bijective proof. Okay, so these are often very difficult to construct. So nice bijections are rather difficult to construct in general, but when they exist, they often give very illuminating proofs of why two numbers must actually be equal. Okay.